Hello, and welcome to my first demo for the SWENG 894 Capstone project. My name is Chris Bassani, and today I will be presenting Crypt. The project is a top-down action roguelike game vertical slice that's developed in Unity. The main gameplay loop focuses on starting a run, entering a procedurally generated dungeon, moving through connected rooms, fighting enemies, collecting item pickups, and ending the run through death, quitting, or clearing the final room. The project is intentionally scoped around a single dungeon floor using a 4x4 grid layout. Each system is evaluated carefully to determine the appropriate level of implementation needed to keep the workload realistic while still supporting replayability. For example, core systems such as items and enemies will include a limited number of variations, allowing their functionality to be demonstrated without expanding the scope of the features beyond a reasonable timeline. This focused approach keeps the project achievable while still demonstrating the core goal of delivering a full gameplay loop. The project uses an agile development approach with iterative prototyping, sprint planning, playtesting, Git conversion control, and modular Unity architecture. Stretch goals such as complex boss fights, additional enemy types, expanded item pools, save functionality, and more dungeon themes may be added, but only after the core gameplay loop is implemented, tested, and documented. You can see here how the conceptual game loop for a single run in Crypt operates. This is how the player progresses through the core gameplay experience in its current conception. The run begins at the main menu, where the player selects the option to start a new run. The game then creates a randomized run state using a generated seed, which controls the randomized elements of that run. Within the current project scope, this includes a 4x4 dungeon floor with starter, enemy, trap, and final rooms, along with items, treasure chests, enemies, and room configurations. By tying these systems to the seed, each run can feel unique and interesting. Once the dungeon is generated, the player enters the main room loop. This is the repeated gameplay pattern of the application. The player enters a room, fights enemies or avoids hazards, collects loot, and then transitions into another connected room. Loot can strengthen the player's stats, while keys can be used to open chests found throughout the dungeon, which can offer even more loot. This loop continues until the player dies, quits the run, or reaches and completes the final room. The bottom left section of the slide also includes a more detailed, high-level domain model that shows the main systems supporting the gameplay loop. At the halfway point of development, several major parts of this loop have already been implemented. Later slides will show which systems are currently functional, which areas still need additional development. This is the current system architecture for Crypt. This is a Unity-based single-player game project centered around utilizing the Unity engine runtime, which acts as the main container for the game and manages how the major systems interact. The application layer contains the higher-level systems that support the game experience. Many of these systems are supported by Unity's built-in features, but I connect my own scripts and logic into them to make the game behave the way the project requires. The gameplay systems layer is where most of the core project-specific functionality lives. These systems are designed to be modular so that each major gameplay feature can be developed and tested separately while still integrating into the larger game loop. The content and data layer contains the assets and configuration data that supports the gameplay systems. This layer helps separate the actual game content from the logic that uses it, which makes the project easier to modify as new items, rooms, enemies, or assets are added. Unity was chosen because it is a widely used and well-documented game engine with a strong support for 2D development. Since this is my first complex solo game project, Unity's documentation, editor tools, and existing runtime systems made it an easy choice for building the game within the timeline available. Overall, the architecture has stayed fairly consistent since the beginning of the project. The biggest architectural change has been in the content and asset pipeline. With approval, I began integrating AI-generated assets into the project. This improved my ability to create consistent sprites, UI elements, and other visual content more efficiently rather than relying on third-party asset websites, which often had assets that were either too specific, inconsistent, or difficult to adapt to the project style. So, while the architecture is not incredibly complex at this level, the structure supports the main needs of the game in a way that can continue to scale it as the project grows. For this project, the main quality attributes are modifiability, performance, testability, and usability. For modifiability, the architecture separates the Unity runtime into the application layer, gameplay systems layer, and content and data layer. This means that changes to rooms, enemies, loot tables, UI, or save data can be made without forcing major rewrites in unrelated systems. For performance, the most time-sensitive behavior is kept inside focused gameplay systems. Movement is handled by the player controller, attacks and damage by the combat system, enemy decisions by enemy AI, collisions by the physics and collision logic, and run state by the game data model. This makes it easier to isolate and optimize any area that affects responsive gameplay. For testability, the same separation makes the game easier to validate. Movement, combat, room generation, traps, chest interactions, item rewards, and run ending conditions can each be tested through the system responsible for that behavior instead of being mixed together in one large script. This is validated in the unit testing cases that are utilized through the project as they're unreliant on anything outside of their scope tasking. For usability, the application layer supports the player-facing experience through input, the HUD, audio feedback, and scene management. These systems will work with the gameplay layer so that the player receives clear feedback for health, keys, items, chest rewards, and overall run state. The architecture was shaped by these quality requirements. The layering shown in the architecture diagram is not just for organization of components, it directly supports how the system can be changed, optimized, tested, and understood by the player. This system is designed for players who enjoy video games, especially fans of action roguelikes. The roguelike genre has a large and dedicated audience, with successful games such as The Binding of Isaac, Hades, Dead Cells, and Enter the Gungeon, which have showed how procedural generation, randomized runs, and replayable systems can create engaging gameplay experiences. The reason I chose this project is both personal and technical. I have been playing games for most of my life, and I have always been interested in how game systems are designed and built. However, game development like this involves many complex areas, including procedural generation, collision systems, combat logic, enemy behavior, and player progression. This Capstone project gives me the opportunity to apply the software engineering skills that I have developed over a decade to a project that is both technically challenging and personally meaningful. The system will be used as an entertainment-focused vertical slice of a larger game concept. Again, the goal is not to build a fully finished game, but to create a complete and playable gameplay loop with foundational systems in place. By designing these systems in a modular way, the project is hoping to demonstrate a working concept while also leaving room for easy future expansion into a larger and more complete game. For Sprint 1, my main focus was establishing the foundation of the Crypt project and getting my first playable pieces of the game working together. I began by setting up the Unity project structure and creating the basic foundation needed to support the rest of the development. From there, I implemented the main menu and new run flow, so the player can start a game session from the main menu and enter the gameplay scene. Once the project structure and run flow were in place, I moved into core gameplay functionality. This included player movement and input, which allows the player to move around the game scene, as well as the initial attack and damage system, where the player can fire projectiles and damage enemies. I also completed the first version of the HUD, which tracks key player information such as health, keys, and items. Alongside that, I implemented the run stats and data model, which gives the project a back-end structure for tracking and modifying player stats during a run. Finally, I defined the initial loot configuration system, which establishes how in-game item data is organized and prepared for future item pickups and gameplay modifiers. Originally, Sprint 1 was planned for 9.5 sprint points. By the end of the sprint, though, I completed 11.5 sprint points. The additional work came from pulling forward some early Sprint 2 functionality once the core foundation was stable. Overall, Sprint 1 was successful because it moved the project from setup into a working gameplay prototype with the major building blocks now in place and put me slightly ahead of the work curve. For Sprint 2, the project continued to make strong progress beyond the original sprint plan. The sprint was originally planned for 10 sprint points, but by the end of the sprint I completed 13 sprint points, which was good to see. A major focus of this sprint was moving the game beyond basic foundational systems and turning more of the planned features into actual playable functionality. One of the first completed areas was the implementation of in-game items and displays. Items were no longer just configuration data. They became usable in-game features that could be shown to the player and tied into the gameplay experience. I also completed the pause menu and expanded run information, which gives the player more visibility into their current run state. This supports both usability and testing because it makes it easier to confirm the stats, items, and other run information as they are updating correctly. Another major piece of progress was the dungeon grid generation. The game now supports a 4x4 grid of rooms, which establishes the structure needed for the procedural dungeon experience. Along with that, I implemented room types and transitions, so rooms can be assigned different types like starter, enemy, trap, and final room types, and the player can move between rooms through doors freely. Sprint 2 also included a significant UI overhaul and code coverage improvement. This helped improve the presentation of the game while also strengthening the project from a testing and maintainability standpoint. Finally, I completed the preparation and creation of this demo, which is important for showing the current state of the project and explaining how the work completed so far connects back to the sprint goals, requirements, and overall Capstone plan. Sprint 2 was successful because it expanded the game project from a basic playable foundation into a more complete gameplay structure. The sprint exceeded its planned velocity, added major dungeon and item functionality, improved the user interface, and strengthened the project through better test coverage. At the halfway point, here are the high-level project use cases that are complete or demonstratable. The current application features can start a run, move the player, perform attacks, track health and stats, damage enemies, apply item effects, update key count, display basic HUD information, generate connected dungeon rooms, and transition between those rooms. Some requirements are partially implemented, like AI enemy behavior, which will be expanded and finished in an upcoming Sprint 3 story. Trap rooms and final rooms exist as foundational concepts in the room configuration code, but the gameplay behavior for traps in the final room are not yet finished. How I am documenting and creating the testing methodology for Crypt is through the flows you can see here. The software architecture describes the quality attributes and functional structure of the system, and this testing approach shows how I verify that the important parts of that architecture are actually working. The first artifact is the traceability matrix. This is the backbone of the testing process because it connects each use case, functional requirement, user story, architecture element, commit, test ID, test commit, test status, and any other comments. The goal is to make sure that testing is not random or disconnected. Every test should be traceable back to a requirement, a part of the architecture, and the code changes that implemented it. The second artifact is the test case specification. Once a test ID exists in the traceability matrix, the test case specification explains the details of how that test is performed. It includes the test type, preconditions, input, execution steps, and expected output. This makes each test repeatable and easier to review and is separated out from the traceability matrix to support requirements from test functionality. For my current approach, every user acceptance test is intended to have a one-to-one relationship with a unit test. Each UAT tries to represent a critical behavior that the system must support, and the matching unit test is the automated proof that the behavior works. This includes critical areas across all the core gameplay systems. Here we have 3 concrete examples of UATs that are especially important to the system. The purpose here is to show that the UATs are not just another checklist, but are connected to critical gameplay behavior and backed by actual unit tests. The first example is UAT 10, Stat Modifiers Update Player Stats. This is important because the item systems depend on stat modifiers correctly changing the player stats. If this test fails, then items may still appear to exist in the game, but their effects may not actually update the player correctly. That would also weaken a core part of the game if the underlying stats being updated correctly were not being processed. The second example is UAT 29. Generated rooms are connected. This validates the dungeon generation system. For a roguelike room progression system, it is not enough to simply generate rooms. Those rooms also have to be reachable and maintain their grid-like connections. If this test fails, the game could create a dungeon layout where some rooms cannot be accessed, which would break progression and undermine the procedural dungeon requirement associated. The third example is UAT 34, projectile hits matching target. This is important for combat validation. A projectile could still be created and displayed on screen, but if it no longer damages valid targets despite hitting their perceived physics hitbox, then the combat system is functionally broken. This test helps confirm that the projectile interaction is actually connected to damage behavior in target validation. Each other UAT not shown represents a meaningful acceptance condition, and the matching unit test provides the automated validation for that behavior. Without these tests in place, I would have less confidence that future changes would not break critical system functionality. These tests act as regression indicators for the most important parts of the project as the codebase continues to evolve. Before we go into the demo portion, I'd like to do an overview of the asset pipeline that has been used for the project. At this point in the project, almost all of the visual assets are being generated with GPT 5.5. That includes the animations, sprites, main menu screens, and textures that make up the current look of the game. For audio, I use Suno AI Music to create 3 major soundtrack pieces: the main menu music, the general in-game music, and the boss fight music. These tracks help give each major part of the player experience a different tone while still supporting the same dark roguelite atmosphere. The menu interface is handled separately. For that, I'm using a third-party resource called Bloodlines Dark UI. This gives the menus a more polished dark fantasy visual foundation and helps keep the menu screens consistent. The reason this asset strategy matters is that I am building this project as a solo capstone. Originally, I expected to rely more heavily on third-party asset websites, but many of those assets were either too specific, inconsistent with each other, or difficult to adapt to the exact style of Crypt. Using GPT 5.5 for visuals and Suno for music has allowed me to iterate faster and create assets that are better matched for the game I'm building, while the Bloodlines UI resource gives the menus a professional structure to build from. For the demo portion, I'm going to start by walking through a few of the workflows and processes I use to manage the project. After that, I will move into the testing and gameplay demo to show the current features that have been implemented. This is the current Jira backlog that I use to organize and track project stories. At this point, Sprint 2 is complete and all of its stories have been moved into the done state. From this view, I can also see the planned work for the remaining sprints, as well as backlog items that have not yet been assigned, including several stretch goals. The remaining Sprint 3 and Sprint 4 work is still flexible. These items may shift as the project continues, since I review and groom the backlog each week based on progress, new risks, and any changes in project priorities. This is the active sprint view, which is where I spend most of my time during development. I use this view to move stories through the workflow and track time against each item. At the start of a sprint, stories begin in to do, then move into in progress as work begins. Once implementation and verification are complete, they're moved into done. Before closing each story, I also attach the related GitHub commit to the Jira issue. You can see that here in the work log. This helps preserve traceability between the planned work, the implementation, and the final sprint report. These backlog and active sprint views are the two Jira views that I use most often, but I also use the reporting tools to generate artifacts for project tracking. This is the Jira reports view. I primarily use this section to generate burned out charts for my weekly report. You can do that by clicking this button here. Sprint reports are also useful because they provide a clean summary of completed sprint work, especially after a sprint has been closed and it's no longer just as easy to review from the active board. Right now, we can only see Sprint 1 and Sprint 2 for the sprint reports. That covers the main Jira workflow I use for backlog tracking, sprint management, time tracking, and reporting. Next, I'll move into the Unity side of the project to show how I handle playtesting, unit test validation, and code coverage reporting. This is the Unity project editor. I'm currently using Unity 6 for gameplay testing, with Visual Studio Code connected to the project for writing and editing scripts. This view gives me access to several important parts of the development workflow. At the bottom, I can view the project files and assets, including sprites, UI elements, and other resources used in the games. Selecting an asset opens an import and configuration settings, which allows me to adjust how it will be used in the project. The Play Mode button up here is also one of the most important tools in this view. It launches the game in its own current state, allowing me to quickly test new features, verify changes, and catch gameplay issues during development. I'm going to wait to launch the game until the gameplay demo portion, but this is the main way that I perform hands-on validation inside Unity. Unity also supports my testing and code coverage workflow. From the top menu, I can open the test runner through Window, General, and Test Runner, which allows me to run the project's unit test directly against the current code base. I run these tests after significant changes and before committing code to make sure existing functionality has not been broken. If I run the tests here, we can see that all of the 78 tests that ran passed. If we expand this out, we can see that it's broken out into the different types of tests that are associated, and all of them are run every single time before I commit any of my code. These tests help validate core systems, and Unity can also generate a code coverage report that shows how much of the code base is currently covered by automated testing. This is the automatically generated code coverage report from Unity's testing framework. Since this functionality is built directly into Unity, I was able to use it without needing a separate setup process. The key areas I focus on are the generation date, coverage history, line coverage, and method coverage. The coverage history can be useful for tracking progress over time, although I cleared the history for this session, so there are no previous results shown here. Line coverage here is the main metric I am tracking, with the goal of reaching at least 70%. At this point, the project is comfortably above that target. I also like to expand the namespace here so I can review coverage at the individual system level. This makes it easier to see which parts of the project are well tested and which areas may need additional attention. Overall, I'm pretty happy with the current state of testing and plan to keep coverage at this or above the level as the project continues. Now we can finally move into the gameplay demo. For this demo, I wanted to test exporting the game as an exe, so this version is running as a standalone application rather than only inside the Unity editor. The main features I want to demonstrate are starting a run, generating a dungeon, moving and attacking with the player, collecting items, displaying run information, and ending or exiting a run. So with that said, let's start it up. When the application launches, the first thing you would probably notice is the main menu music. The track is currently about 50 seconds long and loops when it reaches the end. The main menu has 3 buttons: New Run, Continue, and Settings. The Continue button is currently non-functional, as you can see here. As saving and continuing runs is outside the current implementation of the project. If we click the Settings menu here, you can see that the Settings menu currently focuses on audio control, which lets me keep the game sound from becoming overpowering. Additional settings may be added later, but they're currently not planned. If I turn the master volume all the way up here, the music get louder. If I turn the master volume up and the music sound down, you can see it also gets louder, so you can see that it's fully functional here. The game sounds are currently for in-game sounds, so you won't be able to see it affected here, but it does work the same. When I select New Run, the game starts in the first dungeon room. The background music changes to the dungeon track. I did not personally compose the music. It was generated using Suno AI through several prompt iterations. I think the result fits the dark roguelite tone of the game pretty well, and I ended up liking it a lot. Once the player spawns, movement is handled with WASD in the 4 cardinal directions. For testing purposes, the starting room currently spawns 4 collectible items. Each item applies a different effect to the player's stats. So, the pause menu provides more details about the current run state, including collected items, item descriptions, current stats, key count, and health containers. If we hover over the items, we can see that hovering explains their effects, while the current stat panel shows how the player has been modified during the run. In this example, we can see that our current stats are 2, damage 2, movement speed 5, and attack speed 1. The spinach currently increases your damage by 1, which makes sense because the base stats of the player have a damage stat of 1, so when you add 1 to that, you get 2. So if we unpause here and we pick up the rest of the items, we can see all of these different item effects. 1 max heart, 1 movement speed, plus 2 attack speed, and you can see that all reflected in the health and the current stats. The player can also attack by left-clicking. The fire rate is controlled by the player's attack speed stat, so holding the button down or clicking faster will not bypass the intended attack rate. As the player moves through the dungeon, different room configurations become visible. So if we start moving through these rooms, we can see that we have that was an enemy right there in the test enemy for the test enemy room. The dungeon uses a 4x4 grid, so not every room has doors on all 4 sides. Some rooms are limited by the dungeon boundaries in addition to the starting room. The current build includes enemy rooms, trap rooms, and a final room. Enemy rooms currently has a respawnable test enemy that shoots at the player, so if I'm going to move back into this and move back into this room, you can see that the enemy respawns over and over again, and also that it tries to attack you on your current position. Trap rooms are marked by a red rectangle in the center of the room, so we just found one right here. This is going to be a trap room. This is eventually going to have different traps and enemies configured for the room in its final implementation. And then finally, we have the final room, which is also known as the boss room, and that would be distinguishable from outside by special archways above the entrances. So let's see if we can find one of those. Okay, we got ourselves a boss room here. And once players enter it, the room is marked with a yellow square, and the music transitions to the boss track. So if we just wait a couple seconds here, you can hear the special boss music playing. And if we leave the room, we can hear a transition back to the dungeon music. Lastly, we can lose the run by losing all of our hearts. So if I were to let this test enemy shoot me about 8 times, since that's how much health we have, you would see that we go back to the main menu. So the other option is, if we start a new run here, if you go into the pause menu, there's also a quit run option, so you have multiple ways to end your run if you need to. Currently no way to save it, but that is a stretch goal that we're looking at getting done by the end of the project goals. And yeah, that currently wraps up just about everything that we have for the in-game features and the demoable features themselves at this point. I wish I could showcase some more substantial gameplay loop, but I am very happy with where the game is at after only 2 sprints. And now I think we can move into the wrap-up. We're getting pretty close to the end of the presentation, so we're going to start getting into the wrap-up, and we're going to talk about the sprint, burn down, and velocity. For Sprint 1, the burn down chart shows strong early progress. I committed 10 times during the sprint from May 24th to June 16th, which shows consistent development activity rather than waiting until the end to integrate work. By June 8th, all planned Sprint 1 work was complete, leaving a full week remaining in the sprint window. Because of that, I pulled an additional work from Sprint 2 and used the remaining time to move ahead of schedule. Overall, the sprint velocity exceeded the original plan while still keeping the project aligned with the broader backlog. For Sprint 2, the overall progress remained strong. I made 7 commits against June 16th and July 6th, which again shows consistent development activity against the sprint backlog. I completed the originally planned sprint work early, but the burn down chart does not fully capture the additional work that became necessary near the end of the sprint. By this point, I had accumulated some UI and asset-related tech debt because some of the visuals in the project were still placeholder, and at this point they were implemented, but they were not ready to be finalized. So using assets such as basic colored objects or temporary assets were in place. I also committed to improving code coverage to at least 70%, which required additional testing and refactoring work. I was able to get this up to 79%, thankfully. Another area I underestimated was the time needed to prepare for the demo itself. I had been heavily focused on development, so demo preparation was not fully accounted for in the original sprint capacity. Because of that, the chart does not tell the full story of Sprint 2. Even with the added work, the sprint still resulted in significant progress, and I completed more than the original planned stories while improving the project's overall presentation, test coverage, and readiness for demo needs. Looking at the work completed across the first 2 sprints, the project is in a strong position. I completed 24.5 story points against an expected capacity of 20 points, which shows that the current pace has been higher than originally planned. Going forward, I plan to adjust sprint capacity from 10 points to 11 points to better reflect velocity so far, and I'm going to update the JIRA by shifting items between Sprint 3 and Sprint 4 to align with the new capacity in the future, while continuing to evaluate whether this adjustment remains realistic before Sprint 4 begins. Overall, the project is in a good state, and Sprint 4 still contains a significant buffer currently allocated to stretch goal work. As far as overall progress goes for testing and test traceability over the past 6 weeks, for all the functionality and testing that was demonstrated earlier, the use cases stand as 7 being complete, 1 partially being complete, and 3 not yet complete out of the 11 total. For the functional requirements, there are 19 total. 9 are complete, 8 are partially complete, and 2 are not yet. There are 35 user acceptance tests that have been mapped to use cases and functional requirements throughout testing so far. One clarification I want to make is that earlier in the project I was including some manual verification tests inside the UAT section. I have now separated manual tests from the user acceptance test section so that the UATs are treated as an actual acceptance tests with clear traceability back to use cases and functional requirements after getting feedback from the professor. Because of that change, I still need to reorganize some of the existing UATs from before the switch. The goal is to make the final test documentation show the correct number of actual UATs and to make sure that each one has proper traceability to the requirement it validates. To close out, Crypt has made strong progress across the first half of the Capstone. The project now has a good functional basis to work with that gives confidence that the rest of the project can be completed within the next 6 weeks. While there is still work ahead in the remaining sprints, I feel strongly that the position I am in to continue expanding toward a more complete and polished MVP is completely within sight. Thank you for watching the first demo for Crypt.